The country that lands on the moon first will shape the rules of engagement in space for decades to come. Both the United States and China are working to put their astronauts on the moon in the next few years, with NASA's acting administrator claiming that America will win the race. But what happens if China prevails? NASA plans to launch its Artemis 2 mission to send astronauts around the moon and back early next year, and follow this up with the Artemis 3 crewed moon landing in 2027. China, meanwhile, has committed to making its first crewed lunar landing before 2030 and has recently announced progress on the hardware it needs, including the Long March 10th rocket and Lanyue lunar lander. Pause for a few seconds and support me with a subscribe. Those timelines appear to put the U.S. in the lead, but experts told a Senate Commerce Committee hearing last week, titled, "There's a Bad Moon on the Rise," that America is in real danger of losing the moon race to China. Among the reasons they cited was the pace of development of SpaceX's Starship, which will serve as the Artemis 3 lunar lander, and the need for multiple refueling missions to get Starship to the moon. Unless something changes, it is highly unlikely the United States will beat China's projected timeline, former NASA Administrator Jim Bridenstine told the hearing. If China does land first, there could be profound repercussions for the United States, according to Mike Gold, president of Civil and International Space at Redwire, and a key figure in formulating the Artemis Accords. Let me put you this way: China lands on the moon. The next day, we see tremendous benefits for them, politically, where our eyes turn to them, not only for space exploration, but for national security agreements, for trade agreements, Gold said in response to a question on the importance of landing first. The meeting that's occurring now between China, India, and Russia that you're seeing today. If China lands on the moon first, that will deepen and strengthen those economic ties, Gold added. China is very good at leveraging space to drive the dynamics that Jim Bridenstine and the General Lt. Gen. John Shaw are talking about, he continued. If they get there first, we will see a global realignment that will impact our economy, our tax base, our ability to innovate, and our national security in terms of diplomacy and geopolitics that will affect security and many other aspects of our daily lives. The warning is stark enough in terms of the United States and its leadership in space and on Earth. Beyond a showcase demonstration of capabilities, however, a more lasting impact may be made by the country or countries that establish a sustained lunar presence. Whether or not the prize for landing astronauts on the moon for the first time in the 21st century is a favorable shift in geopolitical dynamics, there may be tangible goals within reach on the moon. Gold, in his submitted testimony for the hearing, stated the following: "If America isn't the first to return to the moon, we risk ceding the best ice reserves to China," adding that this resource can be split into oxygen and hydrogen for fuel, or used for drinkable water. However, the indications are that China is working first toward a crewed mid-latitude lunar landing, rather than targeting the lunar South Pole where water ice is believed to be relatively abundant. At the same time, China's robotic Chang'e 7 and Chang'e 8 missions, launching in 2026 and 2028 to 2029 respectively, will aim to land at key spots near the lunar South Pole and prospect for volatiles such as water ice, and test out the ability to print bricks that would enable the construction of lunar habitats. Alan Cutler, President and CEO of the Coalition for Deep Space Exploration, noted in his testimony that whoever emerges as the leader in lunar exploration will set the rules for the rest going forward in terms of the use of space resources, lunar governance, and the formation of international partnerships. The country that lands on the moon first will shape the rules of engagement in space for decades to come, Cutler said. That leadership must come from the United States. How China's moon plans and NASA's Artemis program progress going forward is going to be one of the most keenly followed and possibly consequential space events for decades, potentially reshaping dynamics on the Earth and Moon. Let's pause for a few seconds and give me a like for this video. Thank you so much. The only way to create a sustainable program of exploring the Moon and Mars with humans beyond the initial flush of achievement is by fully integrating science into our planning. We won't be able to answer the important science questions without human missions, and we can't fly the human missions without science support from the robotic program. Because they need to work together, we should have a single space exploration program that integrates both the human and robotic components. Over 3 administrations, the NASA justification for sending humans into space has been a triad of co-equal components: scientific exploration of the world around us, inspiring us with audacious challenges that excite young people and draws them into scientific and technical fields, and creating a national posture that allows us to develop new technologies and businesses and to exert leadership and influence around the world. The current structure of the human Moon and Mars program has not integrated science in an effective way into the planning process, but there still is time to make that happen. Together, the human space program and the robotic science program can address our objectives. Ensuring that we have a coherent and integrated program that addresses our goals is especially important today. With dramatic changes in NASA's plans for human exploration, and with proposed massive cuts to NASA science, as outlined in the President's budget request. Within our own solar system, NASA's robotic exploration program has been exploring the nature of planets and their atmospheres, their formation and evolution, the materials from which they formed, and how planetary systems work. Both in our solar system and beyond, we are focused largely on finding habitable environments in which life could have existed, and on determining whether there is life elsewhere. Separately, the NASA program of humans in space began as a Cold War effort, but has evolved significantly, especially since the end of the shuttle era. The short-term goal for humans is embodied in the Artemis program to return astronauts to the Moon using commercially provided human landing systems. The long-term goal is to send humans to Mars. However, we feel that these human missions should aim higher. Beyond just sending astronauts, these missions can allow deep exploration of both worlds. We expect that human exploration of the Moon and Mars will be necessary to answer our most important questions about planetary evolution and the occurrence of life elsewhere, as humans have capabilities far beyond those of robotic spacecraft. Our eyes and our brains, and our ability to take in information, process it, and reach conclusions about what we are seeing cannot be duplicated using robotic spacecraft, even with support from from large teams of scientists back here on Earth. At the same time, robotic spacecraft have the ability to explore more places more cheaply than with human missions, all without risking human lives. But they are slower, taking years to do what an astronaut could do better in days, and can carry only a very limited number of scientific instruments. Plus, plans typically are locked in years in advance. Our program should not be an either-or. Human explorers could carry out scientific investigations that go way beyond what robotic missions can do, and they inspire us in a way that robotic missions cannot. But this can happen only if science is built into the architecture and mission planning from the beginning. And it can happen only if a vigorous program of robotic missions supports the human missions through the necessary activities of helping us develop the scientific goals or objectives to carry out, identify landing sites and plan astronaut traverses, and assess hazards and risks. Having a single program will require combining human missions and science from robotic missions in a way that NASA is not doing today. The person leading development of the Artemis and Mars human programs must have responsibility and authority as well for the science to be carried out by them, and they must fully embrace that role. Only then can the science and the mission architecture and hardware be integrated effectively. This integration should start with the return of samples from the surface of Mars to the Earth, both for the science it will return and as a necessary component of risk reduction in preparing for sending humans to Mars. And we should maintain a vigorous Moon and Mars robotic program both for the sake of science and to support the human program. We have the opportunity to design and implement the Moon and Mars programs so that they will contribute substantially to all of NASA's goals for exploration of the solar system. We shouldn't sell the program short by stovepiping the human program as being separate from the robotic program, or by cutting science to below a viable level. If we do, we'll get cool photographs from Mars, but little else. Bruce Yakosky is an emeritus professor and senior research associate at the Laboratory for Atmospheric and Space Physics, University of Colorado Boulder, has almost 50 years' experience as a Mars researcher, and was the principal investigator of the MAVEN spacecraft mission that has been orbiting and exploring Mars for more than 10 years. Scott Hubbard is the former director of NASA's Ames Research Center, was the first NASA Mars program director, and has been active in space exploration for more than 50 years. Now a semi-retired member of the Stanford Department of Aeronautics and Astronautics faculty, he founded the Stanford Center for Commercial Space Transportation and the peer-reviewed journal New Space. Why Send People Back to the Moon? During my PhD in astrophysics, I heard answers ranging from because it's cool to for humanity's long-term survival. But the rarest response I ever heard was for science. Even among astronomers, the idea of human space exploration is sometimes not taken seriously. If we're going back to the moon for the sake of science, some argue, wouldn't we just send robots? It's easy to see crude missions as all sizzle and no steak. They're flashy. They involve boots on the ground. Robotic missions don't tend to conjure the same feelings of national pride and personal inspiration. As Neil deGrasse Tyson once wrote, nobody's ever given a parade for a robot. Nobody's ever named a high school after a robot. Because of their relatively understated nature, you might assume that robotic missions are more scientifically impactful than crude ones. In the end, though, it all comes down to one question. What can Neil Armstrong do on the moon that a robot can't? The answer, it turns out, is quite a lot. If all goes according to plan, NASA's Artemis program will land astronauts on the moon in 2027, then aim to build a sustained human presence there over time. Eventually, NASA hopes to establish a research base and a moon-orbiting space station. None of these grand plans to send people back to the moon are made redundant by Apollo. Humanity has only spent about 12 days' time on the moon's surface, and we have accomplished just a small fraction of the science that awaits us there. It would be a little presumptuous of us to think, been there, done that, about the moon already. I wouldn't feel that way about a country after 12 days, let alone an entire world. And the moon isn't just any world. It's a nearly pristine record of the solar system's past, and a window into how Earth formed and developed life. The surface of the moon is itself an ancient artifact, preserving billions of years of collisions with asteroids and comets. By studying the moon up close, we can learn how impacts shaped the early solar system and potentially delivered life's ingredients to Earth. Likewise, asteroid impacts with the ancient Earth could have left pieces of our planet on the moon, like time capsules for future explorers to find. This is where astronauts come in. Exploring a new world typically means two things: collecting samples and using instruments to gather data. Compared to robots, humans are sometimes better at both. Take sampling. Rovers like NASA's Perseverance are marvels of technology, but they have to be carefully controlled by experts on Earth to know where to go and what rocks to collect. Astronauts, on the other hand, can be experts themselves. They can make their own decisions and think outside the box, spotting unusual features and reacting to the unexpected. Muscles matter too. Astronauts simply can pick up bigger rocks than rovers can, and can pick up rocks faster too. Each of the Apollo moon landings returned with over 10 times more samples than a typical robotic mission brings back. These rocks are a steady source of discoveries for scientists around the world, so the more we have, the better. Astronauts can also get around faster than robots, because, despite what you might think, humans are often better drivers. Robots have a hard time navigating rough terrain on their own. But if you give an astronaut a car, they can easily avoid potholes and boulders on the moon. That means visiting more places and collecting samples farther afield. The crew of Apollo 17, for instance, drove roughly 35 kilometers, about 22 miles, on the moon over 3 days. Traversing that same distance took NASA's Opportunity Mars rover more than 8 years. Gathering data on another world sounds like something you could automate like a farm. But in many cases, it turns out to be more like running a garden, something that takes a delicate touch and a sense of nuance. That's where people work best. Any experiment that requires careful handling, scouting, or setup is almost always better left to astronauts. The instruments slated for Artemis 3, the program's first moon landing mission, are perfect examples. Astronauts will have to carefully pick plants in a terrarium-like experiment, scout the ideal location for a soil probe, and adjust a seismometer to be in perfect contact with the ground. These tasks would be difficult for a robot to do, but are relatively simple for an astronaut. Bigger, more complex experiments will depend on astronauts even more. Mega projects like large drills, huge telescopes, and sprawling factories to extract resources may all need more construction and troubleshooting than robots can do on their own. This is why many people imagine a future for lunar exploration, at least with anything resembling current technology that depends on crewed missions. This doesn't mean humans are better at space exploration than robots. Each has its own strengths and weaknesses. Robots can sit and monitor a world for years without getting bored. They make good advanced scouts since they don't complain when there's no air or food. And they can withstand harsh conditions, like the surface of Venus, to explore places where humans may never survive. Crewed missions cost more, but get things done faster. According to some experts, astronauts tend to be up to 100 times more expensive than rovers, but up to 1,000 times more efficient. Stephen Squires, a planetary scientist and principal investigator for the Spirit and Opportunity rovers, has said that an astronaut could finish a day's worth of work for each rover in under a minute. Price is a real downside, though. Artemis is currently projected to cost over $90 billion through 2025, which is the price of around 30 complete Perseverance missions. At the same time, sending humans everywhere a robot could go would be reckless, wasteful, and mind-bogglingly expensive. We don't need an astronaut to travel to Jupiter and be exposed to deadly radiation just to take photos from orbit. And we definitely don't need to send any astronauts on a one-way trip to fly by Pluto. On top of all this, space exploration is difficult and missions fail. Space agencies have to carefully decide when it's worth risking those in the cockpit. For all of those reasons, a successful space program uses robots and astronauts to complement one another. What astronauts learn on the moon may only be the beginning. Artemis could represent the future of crewed space exploration beyond low Earth orbit. If all goes according to plan, it will mean learning how to build habitats, extract resources, and test new systems for communications and life support. We may then be able to send expeditions elsewhere in the solar system. With the lessons learned on the moon, humanity would have a better sense of how to thrive in space. If Artemis ends up being a scientific powerhouse, it won't just be thanks to putting astronauts back on the moon. One of its greatest impacts would come from putting US back on the moon for the long term. If it can successfully build a sustained human presence there for a fraction of the cost of Apollo. After all, what matters most isn't whether exploration is robotic or crewed, but whether it's sustained. Science works best when it's a continuous effort, allowing knowledge to build on itself and unveil new discoveries. So, the real question isn't why we're putting people back on the moon. It's what we'll manage there with both robots and humans together.